second practical demonstration will cover mostly Haskell types. So if you want to start to write some programs in nearly any programming language, so also in Haskell, if you want to start to write programs in Haskell, maybe one of the first things that we need to study is type system. More precisely, what kind of type system is Haskell using. Type system is, let's say, a crucial part of a compiler, and it in fact translates some high order types that we are using in our program to some sort of sequence of bits that are used in the memory. Moreover, the type system produces some type errors, so it will check which operations are allowed or which are not allowed without types. In any programming language, we don't want to use some low-level construct like bits, but we want to move, let's say, to some higher level of abstraction. There are various kinds of type systems. Here we won't cover everything, but in Haskell, static typing is used. So nearly all controls, usually it is referred as type checking. So all these type checking is performed at a compile time by a compiler, and contrary to this can be a dynamic type checking, where this control is performed at a runtime. So in Haskell we'll be using a static type system. Moreover, a type system in Haskell is memory safe, type safe, and so on. So you are unable to perform operations that are not allowed for a given type. You are unable to access memory that is not, let's say, you are unable to touch anywhere in the memory, but only at the memory that was allocated and that is covered or that is used by given types and given values. Finally, Haskell type system is polymorphic. Usually or most frequently nowadays, this terms is used with object-oriented programming languages. Here is some example of polymorphic behavior when the method is chosen based on the object type rather than on the type of the reference. This polymorphic behavior usually enable us to use, let's say, or to reuse a source code. So one code can be used for a different type. An example of a polymorphic function in Haskell can be a function length, where this function can be used to compute the length of any list, a list of any type. You can see that it is a polymorphic type because there is some type variable in its definition. We will be talking about this in more details later. So if you see here on this slide, function length, it has a type definition, and the first parameter contains a, so some variable. In fact, this means that it's a list. You can see that it's a list because of these square bracelets that are used there, and it is a list containing any type. So in fact, you can use this function to compute the length of list of numbers, list of strings, list of cars, and so on. In fact, you can see here some sort of implementation. Without going into some details, we can say that we just need to count 1 for every element of this list, and it really doesn't matter what is the type of the element. We just add 1 for each of these elements. So the same function can be used for list of various types. Moreover, Haskell type system does not only provide some sort of type checking, so it doesn't really only check if we are using these types correctly, but it also implement this type interference. So the type system is able to interfere to compute the types of these elements like functions and so on by itself. So it can automatically extract this information based on your codes, based on the source code. More precisely, Haskell implements this Hindley-Milner type system. So, if we want to conclude this part, so type system in Haskell is very, let's say, strict. All controls are performed by a compiler in a compile time, and a programmer is unable to perform, let's say, any potentially dangerous operations. So all these controls are very strict, and for example, he is unable to access some unallocated memory and so on, things that you can do, for example, in C++. As in other languages, also in Haskell, there are some basic built-in types that cover some most fundamental values that you are using when you are building your applications. On the slide, you can see some basic data types from Haskell. So there are some numbers. These numbers you can divide into integers and floating point numbers, or integral numbers and floating point numbers. Here you can see some examples. So if you write, for example, 1, its type can be int. If you write some floating point number, for example, 3.14, it can be double or float. Here you can also see some basic operators that you can use with numbers, something like plus, minus, multiply, divide, and so on. There are also some functions that you can use with numbers. So for example, you can compute sinus or cosinus, or you can, for example, round a number or things like that. Beside numbers, there are some characters. Here you can see a type char that will be used in Haskell for characters. Character literals are, if you want to write an character literal, you will be using these quotation marks. So in this slide, you can see a character A like an literal, and if you want to use it somewhere in the program, this is the way how to write it. There are some special characters, for example, a new line. These special characters are written after the backslash. So here you can see some example. So if you want to use this special character somewhere in your program, then you need to write in these quotation marks \n for a new line. There is also a special type for Boolean values. For example, if you want to compare two values, then the result will be this Boolean, and its name is bool, and there are two type constructors, true and false. These constructors are used when you directly want to create a value true or false. Also, you can see some basic operators for this type Boolean. If we want to start to write some programs in Haskell, we need to talk about names. Haskell is very strict considering the names that you can use. All identifiers, everything you write, every name you write in Haskell must start with a letter, and this letter can be followed by a sequence of letters, digits, underscores, and single quotes. So on this slide, you can see some examples of, let's say, valid names in Haskell. These names can be divided into two groups. First, there are these values, so names of functions and name of parameters of some variables and so on. These names must start with small case letter, and then there are types. The names for types must start with capital letters. On this slide, as an example, you can see a data type 3. The name of the type is 3. It starts with big T, and then there are two data constructors, so it can be either leaf or node. If we are talking about layout, the basic rule is that Haskell used the indentation to define the scope. So everything, or say, if we informally say some rules about this, everything that has the same indentation is in the same scope. So all functions need to be formatted so they will use the same indentations. If you have some functions that are, let's say, local functions in some other functions, they need to have a bigger indentation, and they need to have the same indentations. This layout or style of program or style of the program is, let's say, very intuitive. If you have some problems, something is not working, and you can see that everything should be fine, so probably you have problem with some spaces before your functions and so on. I won't talk about it in more details. You will see in my videos and in laboratories and so on how to write a program in Haskell. Here there are some examples. So these functions have the same indentations. If you, for example, look at local functions defined after the keyword where, they have the same number of spaces before them, and the number of spaces is bigger than the number of spaces for the outer function. So this is something like a general rule for how to write programs in Haskell. Finally, we know how to how to use some basic data types. We talked about the type system and about the basic program layout and about the names in Haskell. So we are able to write some functions. Function is the most crucial element in Haskell. So in fact, if we are talking about programming in Haskell, we are talking about writing some functions. So the whole program in our case will be a set of functions. So how the function in Haskell looks like. Here on this slide you can see some examples. So first of all, Haskell function can have a type. It is written, first there is a function name, then there is this double column, and then there is the type of the function. If you don't provide the function's type, then the compiler will compute the most general option for the type for you. So as you have seen in previous video, we have tried to implement a function plus, and the compiler computed its type for us. If you see the type definition, then the type definition compose from some types, and these types are divided by this arrow. If you consider the number of these elements, so every function have some return types. This return type is listed as last, and before the return type there are types for parameters. So in our example, there is a function square. It has just one parameter, so it's an unary function, and its type is int, and the function computes a result, and the type of the result is also int. Second function is function sum. This is a binary function. The function compose from or the functions type compose from three types. The input is integer, second or the first parameter is an integer, second parameter is an integer, and the result is also an integer. Beside the type, the function also have some sort of definition. So after the name and the list of parameters, there is an expression that defines the function. In our case, for example, for function square is the n multiplied by n, and this expression in fact defines what the function does. What we can do with functions, in fact, with a function, we can do just one, let's say, operation, one thing, and it's a function application. We can apply the function on some values. So in fact, we put the value instead, these values instead of parameters, and then we can compute the defined expression right side of the function to get some sort of value that will be produced by the function. So here on this example, you can see some potential application of the function square. So first it was applied on some value 5 or on more complex expression, and we can substitute this given parameter, in our case, instead of the variable n in the expression. To try some examples, in our previous video, we have created a function plus. It adds together two numbers. If we open this Glasgow Haskell interpreter, we can load the file. In my case, is video .hs, and then my function plus is loaded into the interpreter, so I can use it. I can put there some values. So for example, 2 plus 3 and 5, and you can see the result. There are of course some built-in functions. For example, we were talking about functions for floating point numbers. So for example, sinus of value 1, and here you can see some result. So this is how you call some functions. Later we'll be talking about partially evaluated functions, but right now you can assume that if you have a binary functions, you need to provide two values to get the result. In this video, I said that you are able to provide the type for the function if you want, and if there is no type, then the compiler computes the type of the function by itself. From this perspective, Haskell type system use some mechanism that is called type classes. So these types are divided into some classes, and each of these class have some operations that can be performed with types from the same class. So for example, if we have, I don't know, numbers, these numbers can be compared. So for example, if I have 1 that is smaller than 2, and the result will be that this is true. So all types that can be compared, all types where values can be compared, are in the class ordinary. And if we want to add a new type into this type class, we need to provide this operation smaller, bigger, and so on. And then values of this data type can be compared between each other. How to view this mechanism in the program? If we consider our function plus, it's the same function or nearly the same function as the function sum from the previous example, but the implementation is the same, but the type of the function is not. If we use the type that was computed by the compiler, you can see that it contains some sort of num. So what is the meaning of this definition? So this type definition can be more complex, and that can be this double arrow, and the real type is defined after the after this double arrow, and before there are some type classes. So this function plus, as we said before, is a polymorphic function because it contains this type variable a, and in fact, informally, the meaning is it can be any number. What is the, let's say, the restriction for the function plus? The restriction for its type comes from this operation plus. In Haskell, the operation plus can be used for numbers. So the compiler computed informally that this function can be used for any numbers. In fact, if we try and if we want to add 5 plus 6, it will work, and it will also work, for example, for 5.5, so for floating point numbers. So the compiler gives us information that this function will be used for any numbers. So the a, the type, can be chosen from the type class num, where are these numbers. Moreover, from the definition, we can see that this type variable is used there is just one type variable in the definition. So it's something like type A, second instance of the same type A, and so on. From this perspective, we can add together only the same types using operation plus. So for example, in our previous case, we were adding two numbers. There was number 5.5 and 6, but 6 can be treated like an integer and also like a double or float. If we define that it will be strictly an integer number, we can do that by this double column. So like that, I'm telling the 6 is integer, then I'm unable to add these two numbers together, because now the first number is a double or floating point number, and the second number is integer. So I have chosen a floating point number for a, so the second parameter is wrong because it's integer and it's not a floating point number. So this is how you can see the definition. It's like a variable, but you will put just one value in one definition, just one value for the parameter, and then the type must hold. One question can be why we need to provide these function types if the compiler is able to compute them by itself. One possibility is what we can do by that is that if we provide the type definition, then we can restrict the function to certain types. So as I said before, for example, for our function plus, if we write it like that, then this function can be used for any number. But let's say that right now we want to use it just for these integers. So we can write the definition directly into our program, and we specify that this function can be used only for the type int. And right now, if we reload the file into the interpreter, right now we can run the function plus only for integer numbers, for example 1 and 2. But if we use a floating point number, it will lead to an error. Before, or if we remove the type definition, for example, we can use this 2 minus characters, then it will be a note. So if we change it like that, I have stored the file using Ctrl S, and I have reloaded the file into the interpreter. If you use it like that, then the previous operation will be fine, because right now it's the type of the function is the same as before, and it allows any number on its input. At the end, allow me one more remark. I have spoken in this video that program in Haskell composes from functions, but at the same time, and only functions, but at the same time, I spoke about operators like plus. So it's not precisely true. You can define functions and operators, but from this perspective, you can treat an operator in Haskell like a function, like a binary function. The only difference, in fact, is in the is how you use it. So operators are written in this infix notation. So you write 1 plus 2 instead of functions. When if you want to apply a functions on some values, first you put the name of the function and then these values. So the only difference is in this notation, and the second difference is in the priority. So if I give you an expression and you want to evaluate this expression, so the important information will be for the evaluation will be about priority of the operation that will be used in this expression. For these basic operations like plus, minus, multiply, and so on, the same priority as in math will be used. We'll be talking about this in more details in the following video, but the basic idea is that operators are defined similarly to functions, and the only difference is that you can define some sort of priority for them, and then this priority is used when expression containing this operator are evaluated.